Just Miller, Rock College Physics here, and we're back looking at some hydrogen atomic systems here. All right, so we have discerned quite a bit about the hydrogen atom utilizing Bohr's model of the atom. Now, I will say a couple things about Bohr's model of the atom. It works. It works for determining the energy levels of systems that involve a single electron. So you can do it for hydrogen like we've done. You could do it for helium, but it has to be singly ionized helium. You could do it for lithium, doubly ionized lithium, and so on. But eventually, once you have more than one electron in the system, it falls apart really quickly. So you start to think about, why would it just work for one electron? Well, if you got more than one electron, you got some problems with the overall energy levels of the system, because you have to look at the potential that both electrons are in the presence of that proton, and have some way of gauging, well, they're in potentials of one another as well. And if they're orbiting, according to Bohr's model of the atom, they're coming into different proximities with respect to one another, and you get a whole bunch of very difficult things to work out. And it turns out that, well, Bohr's model of the atom works well in determining the energy levels of the single electron systems, that it's really not so much like, oh yeah, the electron just goes in this circle and they transition and the light's emitted. That's true to some degree, but it's a lot more gray than that, we'll say. Ultimately, the true or the understood nature of the atomic systems is much more complex. And quantum mechanics ultimately comes along and takes over and says, this is how things are, which we're not getting totally into quantum here. It's very, let's say, almost abstract in a way, that things occupy multiple energy levels simultaneously, all this kind of mind-bending stuff. I'm not going to really worry about that. What we are concerned with, however, is the representation of the energy levels themselves. And that is true for all atomic systems, that there are discrete energies at which the atomic system can reside. And when there is transitions between those energy levels, that's when light's emitted, or possibly absorbed. But if we have an atom or an electron that makes a transition, or that the system, I should just say, makes a transition from a higher state to a lower state, we have light that's emitted, and we can measure the wavelength of that light. The wavelength of that light correlates with the energy difference between the two levels of which the transition occurred, and that's still powerful, powerful to think about, powerful to study. And even though Bohr's model itself has some holes in it, the overall energy quantization is what's really, really important here. So that's what we kind of want to look at here, the energy levels, energy level diagrams. But before we do that, there's one other way that we're going to look at this. Real quick, you generally see in the chemistry class. We almost got there last time, but we'll just finish this up here. So we had the energy levels. The hydrogen atom, E sub H, we're given by negative 606 electron volts divided by n squared. And generally this is actually called E sub n. We're just giving it for the hydrogen atom. We know that n takes on discrete values. N is equal to 1, 2, 3, ... integer values. And then we had the wavelength, the energy of the emitted photon, E sub gamma, was equal then to E initial minus E final. And again, because we're going from a higher energy level to a lower energy level, we want the energy of the photon that is positive, because that's spit out. We take the initial minus the final. So what does this end up giving us? Well, we had written this out before. So it's negative 13.606 electron volts divided by what we could call N initial squared minus negative 13.606 electron volts divided by N final squared. We've got the negative, negative, negative there. We could just flip the order of this and say that E sub gamma, the energy of the emitted photon, is then equal to 13.606 electron volts multiplied by 1 over n sub f squared minus 1 over n sub I squared. That changes order because minus minus plus, there's the minus, and we've got it like this. Well, you've probably seen an expression that almost looks like this, but it's like this. We can write from E sub gamma being equal to hc over lambda, we can write that hc divided by lambda then is equal to 13.606 electron volts times 1 over n final squared minus 1 over n initial squared. And then what can we do with this? We could divide both sides by hc and write this as 1 over lambda is equal to 13.606 electron volts divided by hc multiplied by 1 over n final squared minus 1 over n initial squared. Final step with this is these two values, or the numerator and the denominator, can be combined into one. Of course, we want to be careful with SI units versus electron volts. We can convert that back into joules, divide by HC, assuming that those are in SI units, and we can get this. We can write that 1 over the wavelength is equal to R sub H multiplied by 1 over N initial, and final squared, minus 1 over N initial squared. Maybe you've seen this before. This is the Ryberg formula for the light emitted by the hydrogen atom and going from a higher energy down to a lower energy. This is the wavelength of light, and this is Ryberg's constant, R sub H. Ryberg's constant has a value of 1.097, 1.097 times 10 to the 7th per meter. There's Ryberg's constant right there. What is Ryberg's constant really equivalent to? It's equivalent to this. The ground state energy in joules divided by hc. That's what this comes from. But this is a nice expression that they use a lot in like a chemistry class, that when you're studying hydrogen, the light emitted by hydrogen, you just use that. You got an N initial and an N final, and boom, 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 you figure out the wavelengths, great. But all of this came from Bohr's theory, Bohr's model of the hydrogen atom, which, boom, can be kind of condensed down into that. Pretty cool, yes? Yes. All right, so going back to the energy levels of the hydrogen atom, we can look at what are known as energy level diagrams. And ultimately, an energy level diagram just kind of spells out what are the energy levels, how are they laid out. So they're laid out in terms of these principal quantum numbers here. We've got n equals 1. The n equals 1 is known as ground state, or ground state energy, and this is the negative 13.606 electron volts. Great, ground state. That's where the electron actually wants to be. This is the lowest energy that the hydrogen atom can be in. And generally things want to be at the lowest energy possible. But it's possible that we dump some energy into the atom and we bump up the electron into a higher energy state. So what's the next energy state that's possible? We've got ourselves, that's right, you guessed it, the n equals 2. Well, n equals 2 is the first excited state, often called first excited state. And what do we have? We've got ourselves a value for it. From my calculator, uh-oh. Here it is. Ooh. Got a value for it that would be equal to this divided by 2 squared. So we've got 13.606, oops, 13.606 divided by 4, and negative 3.402. Negative 3.402 electron volts. Put that all in right, 606 divided by 4. That's good. And then what comes up next? Hey, the n equals 3. The n equals 3 state ends up being closer to the n equals 2 because it's going as 1 over n squared. We got n equals 3. We could call it the second excited state, but eventually we just say, hey, it's the n equals 1 state, n equals 2 state, and so on. So this one's going to be our 13.606 divided by 3 squared, which is going to give us 1.512. We'll call it negative 1.512 electron volts. And then we've got the n equals 4 state. The n equals 4 is going to be the 13.606 divided by 4 squared, which is going to give us 0.850. Negative 0.850 electron volts. And then what? Then we've got an n equals 5. And this isn't drawn out to scale, but we get that these energy levels get closer and closer together. The biggest difference is between ground state and this in terms of successive differences. As we look at higher and higher principal quantum numbers, we get that the energies of the atom are closer and closer together. But anyways, n equals 5, 13.606 divided by 25 gives us 0.544, negative 0.544 electron volts. We'll do one more. N equals 6. We could keep on going, but they get kind of too close together. 13.606 divided by 36 gives us 0.378. Negative 0.378 electron volts. And then this keeps going up to n equals infinity ultimately, but eventually E is equal to 0. Gives us that the E electron has been removed. It's become ionized. Say no longer bound. So to completely remove the electron from ground state would mean that we'd have to give it at least 13.606 electron volts of energy, such that the new energy of the system would be 0. The electron would just be unbound from the system. And that's it. This is how this is looked at. So now we sort of look in terms of the light being emitted. Well, each transition is possible. Any transition is possible. Some may be more likely than others, depending on certain circumstances, but ultimately, if we have a large collection of atoms, everything is going to happen, assuming that we're continuously dumping in large amounts of energy. So we could take an electron and say, hey, it's bounced all the way up into the n equals 30-something state. What happens? Well, it's going to want to trickle down, or it's going to want to get back down. It wants to be at ground state. So how's it going to get there? Well, there's all these different ways it could get there. It can go from 36 to 35, 35 to 34, 34 to 33, one by one, or it could just jump from n equals 36 to n equals 1. Or it can go from n equals 36 to n equals 6 to n equals 2 to n equals 1. Each transition, though, is going to emit a photon, emit a particle of light, has a specific wavelength that is correlated with the energy level difference, as we've noted right there. So the question becomes, what wavelengths are the ones that we observe in that visible spectrum? There's only 4 of them. We see a nice red line, and we see sort of a bluish greenish line, and then we see 2 violet lines. And that's it in the visible spectrum. There's a whole bunch of other spectral lines, we'll say, or other wavelengths of light that are emitted, but those are in the ultraviolet and infrared range. So what we want to be able to do is determine which ones are actually, what transitions are the ones that we see with our eyes in terms of the light being emitted. So, how are we going to get this? Well, we could just jump on over to something like the Ryberg formula and sort of figure it out from there, right? That'd probably be the easiest thing to do. So, let us say that we want to look at n final is equal to 1. Look at n sub f is equal to 1. So we're going to be looking at transitions that end at ground state. The largest amount of energy that a photon can have would be a photon going from, well, 0 energy, a photon associated with the electron going from 0 energy all the way down to ground state. And in that case, the photon energy would be equal to this, and we would have ourselves largest energy photon would be going from n infinity to n equals 1. N equals infinity to n equals 1. That gives us the largest energy level difference, and thus the largest energy photon, because they're proportional to one another. So what is the wavelength of light that's associated with this transition? Well, if we've got that 1 over lambda is r sub h multiplied by 1 over 1 squared minus 1 over infinity, not alpha, infinity squared. Final minus initial. Well, this just gives us the inverse of the Ryberg constant would be equal to lambda then. Lambda is then just equal to r sub h to the negative 1, which would give us, let's go ahead and look at that. We've got ourselves 1.097 e to the 7th. Got ourselves 9.116. 9.116 times 10 to the negative 8. There's the wavelength of light for that particular transition, going from n equals infinity down to n equals 1. What is that wavelength? Well, if we move this over 1 decimal place, we could write this as 91.16 nanometers. And ask ourselves, hey, what portion of the electromagnetic spectrum is that wavelength of light? It's definitely not visible. Visible is from 400 to 700 nanometers. This is below 400. This is ultraviolet light. All right, well, let's look at a smaller transition that still terminates on the n equals 1 ground state. We could look at the lowest energy possible for that particular end state, the ground state, and that would be 2 to 1. What sort of realms does that give us? What sort of wavelength does that give us? So now we look at this transition, n equals 2 to n equals 1, and we've got that 1 over lambda is going to be equal to r sub h multiplied by 1 over 2 squared, 1 over 1 squared, minus 1 over 2 squared, and ultimately this just gives us lambda is going to be equal to, we've got 1 minus 1/4, 3/4, 4 over 3 r sub h. So I go 4 divided by 3 times 1.097 e to the 7th. Yourselves 1.215 times 10 to the negative 7. What is that? Well, we can move the decimal place over 2 times and get 121.5 nanometers. And this is still ultraviolet. So, anything that terminates at ground state, any transition that terminates at ground state will always give us some ultraviolet light. There's the bottom line. So we definitely have that the final state being ground state isn't responsible for the wavelengths of light that are witnessed in the visible region of the electromagnetic spectrum. So what can we do? We can go up and say, well, what about the n equals 2? N equals 2 being the final. Now, look at n sub f being equal to being n equals 2. All right, so we can again look at the largest energy. We've got ourselves that n initial would be n sub infinity, and we've got 1 over lambda is equal to r sub h multiplied by 1 over 2 squared minus 1 over infinity squared would just be giving us that lambda is equal to 4 divided by r sub h. So we'll go ahead and take that. 4 divided by 1.097 e to the 7th gives us, let's check this out, 3.646 times 10 to the negative 7 meters, which is then equal to 364.6 nanometers. Still ultraviolet, right? Ooh, getting pretty close to the visible spectrum, but still ultraviolet. So look at the smallest energy level difference that terminates on n equals 2, and that would be n equals 3 goes to n equals 2. Smallest energy level difference possible again. We're terminating on n equals 2. And what do we have with this? Well, we've got ourselves that 1 over lambda again is equal to r sub h multiplied by 1 over 3 squared, 1 over 2 squared minus 1 over 3 squared, which will give us 6.563, 10 in the negative second. 6.563 times 10 to the negative 7 meters. $656.3 nanometers. Is that in the visible spectrum? Yes, it is. It is. This is actually in the red region of the visible spectrum. Red spectral line that we see, the red wavelength of light in the spectra of the hydrogen atom. There it is. It is due specifically to this transition right here. We go up to the energy level diagram and we say, hey, this particular transition, going from n equals 3 to n equals 2, gives us that red light right there being emitted. Anytime that transition occurs, photon with that wavelength is being spit out. All right, so we want the other wavelengths. Well, let's just bump up one and say, well, probably another one's going to be n equals 4 to n equals 2, n equals 5 to n equals 2, and n equals 6 to n equals 2. So we go ahead and we compute those out here really quick. So let us look at those. N equals 4 to n equals 2 gives us 1 over lambda is equal to, again, r sub h times 1 over 2 squared minus 1 over 4 squared, which gives us lambda. And this one will start speeding up here a little bit. Gives us 486.2, we'll say. Nanometers. Which is bluish. Hey. So we know then that the transition from n equals 4 to n equals 2 gives us a blue photon, blue wavelength of light. And we could go on and look at n equals 5 to 2, and that n equals 6 to n equals 2, and we get ourselves the lambdas. Do this here really quick. That goes to 25. Gives us 434, 34.1 nanometers, and the other one's like 411. But calculate it out here, 36, and 410, 410.4. Which are both in the violet region of the electromagnetic spectrum, in the visible region. So we get these 4 wavelengths of light in the visible spectrum that are due specifically to those transitions there. And I may have drawn these out where it gives the interpretation that the wavelength got longer, but actually it's shorter. Well, some things to note: larger energy level difference, shorter wavelength, higher energy. So larger energy level difference gives larger photon energy. Which gives shorter wavelengths. So if we start looking at, say, n equals 7 to n equals 2, n equals 8 to n equals 2, those start giving us values that are back in the ultraviolet region. But if we then go ahead and say, well, let's start looking at energy levels that transition from something higher to n equals 3. All of those end up being infrared. And that's just how that works out. So those 4 transitions are the only ones that give us light in the visible region. And that's exactly what we see when we pass the hydrogen light through a diffraction grating and measure the wavelength to be these right here, 656, 656, 486, 434, 410. That's it. So that's pretty darn cool to be able to make the connection with. All right, so that's pretty much that for the energy levels. It's always just about figuring out the wavelength of light or the corresponding energy, or sometimes figuring out what is the orbital speed in the Bohr theory then, or what is the radial distance away from the proton, which the electron exists in a certain state. But really, this is the most important aspect of it. The energy levels, the energy level differences, the transitions of energy levels, and the photons that are ejected or emitted due to the transition. All right. That was fun. Have a good one. And yeah, don't forget about hydrogen. Hydrate. Take care.